So I thought that the ideas in this worksheet were a little bit more complex, and so I thought I would just go ahead and break it down for you and discuss it. I thought you'd get more out of it. So when we look at this worksheet, it starts by saying in series circuits, electrons have one path to follow, and the current is constant throughout the circuit. Now you may have used a different term than constant, but that's fine. As long as it means the word constant, then that's fine. So in other words, if I'm talking about electrons coming out of my circuit and traveling through, the amount of current that leaves the battery has to travel through each of those loads before returning to the battery's positive terminal, right? And so I know that the current at this position is the same as the current here and here and here. There's no splitting of the current, so therefore I can say that the current passing through the first load is the same as the current passing through the second load and is the same as the current passing through the third load. So in other words, the current remains the same everywhere. If more loads are added in series, the resistance increases because the electrons have more bumps, which cause them to lose energy. Because of this, you might have put the word collisions. Because of this, the light bulbs in a circuit with two loads in series will be brighter than the circuit with a single light bulb. Oops, sorry about the little typo there. Good. Now let's take a look at what happens when we are talking about voltage in a circuit that has its loads in series. Okay, so hopefully you noticed that when you were building your circuits where the loads were in series, that as you added an additional light bulb, each of those light bulbs, got progressively, as you added them, all of them got dimmer, right? So the brightness of the lights decreases as loads are added. And that's because as the electrons move through the circuit, they're going to be losing energy at each load, right? So electrons are, with a certain amount of energy, are all going to go through, let's maybe move them through this load, and they're going to use up a little bit of their energy here, a little bit more here, and then the final remaining amount of energy through the last load, and then they return to their battery in order to get more power. I do want to mention that, and I may have mentioned it in class already, that, there's a difference between what we call conventional current and electron flow. So we might describe electrons flowing from the negative terminal towards the positive terminal of a circuit, of a battery rather. However, before the time we really understood about electrons and negative charges and what was making up current, we considered the electrons, or the charges rather, to be moving from the positive terminal to the negative terminal, and that was sort of arbitrary, right? And so if we talk about conventional current talks about the electrons moving from positive to negative terminal. But if we're actually talking about electron flow is, of course, from the negative end towards the positive end or terminal of the battery, as we would expect, because negative charges are attracted to positive charges. All right, so back to voltage. So, so we can say that the total amount of voltage gets lost through one loop of the battery. In other words, a little bit of energy gets lost in the first load, a little bit more here, and a little bit more here, so that after the electrons pass through all three loads, they've lost all their energy. So the sum of the drops in voltage equal the sum of the gain in voltage at the battery. Okay, so the total equals the sum of the drops. So for instance, let's put some numbers here. So let's say, for instance, the total voltage here was 12 volts. Maybe, there's 4 volts that gets lost here, another 4 volts here, and another 4 volts across this last load. Now, they don't necessarily need to be the same, depends on the resistance there, but in this case, each of those lamps are equivalent. And so once all 4 volts are lost times 3 lamps, the current now has no energy and needs to recharge at our battery. Now let's see how that compares to our current when we're talking about our lamps or our loads organized in series. So we see here that if we're talking about electron flow, the electrons are going to flow through here and hit a kind of a fork in the road. And so those electrons are going to be split into two different pathways, sort of like if you had one big river that split into two streams. And so some of the electrons are going to move through this way, and other electrons are going to keep going, right? So a few of them are going to travel across this pathway. So they have their own pathway here. However, the rest of them are going to travel down here where they might be split again. Now, coming out the other end, the electrons that went through this pathway and those that went through this pathway are going to rejoin each other. And then over here, they're going to be, at this point in the circuit, they're going to rejoin the electrons that pass through this pathway. So even though they get split up in the middle here, they end up eventually rejoining and forming a total current again, right? So I can say that the total current measured at the source is equal to the sum. So let's see how that compares when we're talking about voltage through loads in parallel. So in this case, when I look at this, I see, because each electron travels through only one load, it's able to give all of its energy to a single load before re-energizing at the power source. So remember, when we're talking about voltage, the voltage doesn't get split like the current does. So even though we might have some electrons going in through this path and, another electron going through this path and another electron going through this path, each of those electrons come from the same source. And so, each individual electron is going to have its own path, and it's going to be giving all of its energy towards making that lamp bright. And so, in this case, in this one pathway, this one electron is giving all of its energy to a single lamp before needing to go get recharged. So let's say, for example, that the total voltage here was 120 volts. So let's say the total voltage is 120 volts. So that would mean that an electron that leaves the terminal has 120 volts, but then has only one load to have to give that energy to. And because across that load in a single path, the voltage has to drop back to zero. So 120 volts gets lost here. However, a different electron traveling through the second lamp instead is also going to have to lose all 120 of its volts, right? Volts of its energy. And then the same goes for that same loop. So when we're talking about the total potential difference, if these lamps are organized in series, we know that the voltage across each of them has to be equal. And again, that's because the voltage needs to drop back to zero through a single pathway. Now, this is, of course, only with one load in each pathway, and sometimes we have combinations of circuits in series and in parallel, and that makes things a little bit more complicated. So let's review these ideas. So I want to contrast what happens with current versus with voltage in series circuits versus parallel circuits. So if we're talking about current, we're really talking about the flow of electrons. And so in a series circuit, the electrons have only one pathway to flow through, and so the current will be the same throughout. As opposed to in a parallel circuit, where that current gets split into different pathways. Right? Well, I think that's easier to understand than the voltage. So the voltage, if we're talking about in series, will drop a little bit across each load because all of those loads are in the same pathway. And so the sum of the individual drops equals the sum of the energy gain that's gained at the battery again. In parallel, the voltage is the same through each path if the loads are identical, right? And so you're going to see that in a single loop, in each individual pathway, you're going to see an entire voltage drop back down to zero, so that when the current gets back to the power source, it's regenerated entirely. Let's practice a few examples that will help us to consolidate these ideas. So here's a typical question that you might be asked. It says, well, a circuit contains two identical lamps. The potential difference of the battery is 30 volts. And what would be the voltage drop across each load if the lamps were connected in series versus in parallel? All right. So if I'm talking about in series, then really what I have here is I have, here's my power source for argument's sake. And then, I'm going to have some kind of a load here. I'm going to just make it a lamp. And then another load here. So, maybe visualizing might help you to make sense of this, right? Well, I know that my voltage at my source happens to be 30 volts. But I know that across each of these lamps, I'm losing all 30 volts. So by the time I get back to the negative end, or back to the battery after the electrons pass through the circuit once, all of my voltage has dropped down to 0. So if I know that each of these is an equivalent lamp, then I know that each of them has an equal voltage drop across each lamp. And so, that tells me that the voltage drop across each of them has to be 15 volts each. So because 15 volts plus 15 volts is going to give me my 30 volts at the end. Now let's contrast that with what would happen in parallel. So, I'm going to draw my little circuit over here. Same idea. So in parallel instead, I'm going to have, here's my, a battery, and then I'm going to have a lamp. I'm going to choose one load and then another load here, right? And again, I know that the voltage at the source is again 30 volts. The difference here is that the electrons have two pathways. Oops, look at this circuit. I haven't quite finished it. I need to do that. There we go. So I know that the voltage, an electron traveling through this pathway has to lose all of its energy in that one lamp. And an electron traveling through this secondary pathway also has to lose all of its energy through that one lamp. And so that tells me that the voltage drop across each lamp is going to be 30 volts. So 30 volts if the electron decides to go through this pathway, losing it all on that lamp, and then traveling back to the power source to regenerate, or also all 30 traveling through this pathway. So 30 volts. Let's try another example. So in this question, it says a circuit is set up with two equivalent resistors in parallel. If the total resistance is 2 ohms and the potential difference across the battery is 6 volts, calculate the current through each resistor. All right, well, maybe we should start by drawing a diagram to make this a little bit more visual. So I'm going to set up my circuit here. Oops. And I'm going to set up my resistors in parallel. Here's one resistor. And there's another resistor. Not perfect, but it works. Okay, and I know that the total resistance, I'm going to write R total, happens to be 2 ohms. And I also know that the potential difference across the battery, so in other words, that's my voltage right at the battery, happens to be 16 volts. Right there. Now I want to know what the current is through each of the resistors. So I'm going to call this resistor 1, and I'm going to call this resistor 2 over here. And I want to know what I1 is, and I want to know what I2 is. Okay? So this is kind of tricky, right? So let's talk about ideas first. So first of all, I know that as an electron is traveling across this resistor right here, I know that it's going to be losing all of its voltage to that resistor before needing to get regenerated. So I know that my voltage right here, I'm going to do that in a different color so it stands out. I know that my voltage right here is going to have to be 16 volts. And if I apply the same logic over here to my second resistor, an electron is going to lose all of its energy to that second resistor and need to get recharged. And so the voltage across my second resistor is also going to be 16 volts. That's the potential drop. That's the voltage drop. All right. And so if I want to know what the resistance is, or what the current is through each of those, there's no way for me to know each of those resistors. There's no way for me to know that unless I know what the starting current is, right? And so that's what my first plan of attack is. I'm going to call this step number 1, which is to find the total current. So I know that V is equal to IR, and I can use my triangle to sort out, or just math, to sort out that my current is going to be my resistance divided by my voltage. Wrong. That's going to be my voltage divided by my resistance. My apologies. And so I'm going to sort that out. So my voltage was the 16 volts, and I know that the total resistance across all of it, the whole circuit, is 2 ohms. So 16 divided by 2 tells me that in total, the total current is 8 amperes. So that's my first thing. So I could go back over here and I could say, okay, well, now I can go ahead and fill in that my current having some technical difficulties here, people. Please bear with me. My current happens to be, at the source, is 8 amps, right? So now that I know that, that's going to help me to figure out what the current is through each resistor. Now, since I know that my voltage drop across each lamp is the same, I know that when my current reaches over here, that it's going to be split equally. And so that tells me that the current across my first resistor is going to be equal to the current across my second resistor, and that happens to be 4 amps. So 4 amps are going to move through this pathway, 4 amps through this pathway, then they'll return as 6 amps of current to my source. So that was a little tricky, but hopefully you were able to follow that and make sense with it. Let's try a third example. So a series circuit contains 3 identical lamps. The current coming out of the energy source is 2.5 amps. So now so I can go ahead and start to draw this. I think it's important to get a visual. So I'm going to draw my little circuit, and it's series, so I'm going to draw my lamps in series, and it doesn't matter really how I draw this, as long as there's only a single pathway. And I'm not going to draw a switch just to keep it simple, but here's my third lamp. All right, but really, if I were constructing this, I would want some sort of control device. So it says to me that the current coming out of the energy source is 2.5 amps. So I'm going to call that, I'm going to kind of place that right over here, and I'm going to call that I, and that was 2.5 amps. Here we go. Right, and then so I know that the total resistance, okay, so I'm going to call that RT, is equal to 6 ohms. There we go. And I want to know the voltage across each lamp. Well, in this case, I know that my current at this point in the circuit is the same as the current at this point in the circuit, and so on and so forth. And I know the total resistance. And so my first step is going to be to figure out what the total voltage is. So I'm going to call this VT. So my total voltage is going to be equal to my current at the source times my resistance, my total resistance. So that's 2.5 amperes times 6 ohms. Oops. Right? And so that's going to give me 12, 13, 14, 15 volts. Now, what they've told me is that each lamp is equivalent. So what that means is that the same amount of energy is going to be lost at this lamp, and at this lamp. And then by the time the electron reaches this point, it will have given up all of its energy, all of its 15 volts. So if these are all equivalent lamps, then I take that voltage, right, that 15 volts, and I divide that by 3, and that tells me that the voltage drop across each lamp is 5 volts. And I'm done. So hopefully you found that okay. What I'd like you to do now is notice that there is some homework that's assigned. This is also on Google Classroom, but spend the remaining time that you have completing this homework, and make sure to leave some questions for me should you have any. Save them for Tuesday morning or afternoon rather, and I'll be sure to help you out.